Welcome back to the deep dive. This time, we're
Oh, this is going to be a good one.
yeah, we're wading into some pretty deep waters.
Deep waters.
The Motivic Hilbert Zeta function for curved singularities.
That's a mouthful.
It is, and you sent over a bunch of research papers, notes, all that.
Yeah, quite a bit.
It gets pretty complex.
It does?
But that's what we're here for, right? To unpack it all.
Absolutely.
Find the hidden gems.
That's right. And given your background, I think we can just jump right in.
All right, so the jumping off point here is the Motivic Zeta function of a variety.
Okay.
The source material defines it like this.
Yeah, I see that.
Sim xtionia,
Yes.
xtn key 0 val, vark. Now, I know this might look like a jumble of symbols to some people.
Sure, to the uninitiated, perhaps.
But it's actually a really elegant way to capture information about a geometric object,
I agree.
about a variety X, right over a field K.
Yeah, and the cool thing is it's an invariant of X.
So no matter how we twist or turn X, as long as we don't fundamentally change its structure,
Right.
this theta function stays the same.
It's exactly. It's a powerful tool.
Yes.
But it doesn't tell us everything.
It doesn't.
It's not sensitive to singularities, which are those points where our geometric object isn't smooth,
Right.
like the cusp of a curve,
Yeah, exactly like that.
where it suddenly changes direction.
Precisely.
And that's where the Motivic Hilbert Zeta function comes in.
That's right.
It's defined as Hilbert xt, xtm, xtn, xtm, xt, vark. And instead of looking at symmetric products,
Right.
it looks at the Hilbert scheme of points.
Yeah, Hilbert scheme.
Now, I remember from my algebraic geometry days that the Hilbert scheme is a way to parameterize all the different ways you can stick a certain number of points onto a variety.
Exactly.
So it turns out that this focus on the Hilbert scheme makes the Motivic Hilbert Zeta function sensitive to singularities.
Precisely.
So when X is smooth, the two zeta functions agree.
Right.
But when X has those pesky singularities,
Mm-hmm.
the Motivic Hilbert Zeta function gives us a finer-grained picture.
Exactly. And for reduced curves over a field,
These Motivic Hilbert Zeta functions are rational.
meaning they can be expressed as a ratio of polynomials.
That's right.
That's crucial for actually computing them.
Absolutely. Now, another key point is that for a curve with multiple singular points,
Okay.
we can break down the computation of the Motivic Hilbert Zeta function.
All right.
We can calculate it separately for each singular point and for the smooth part of the curve.
So it's like a divide and conquer strategy.
Exactly.
Very cool.
Now, for this deep dive, we're focusing on a specific type of curve singularity.
Okay.
A germ of a singular curve, denoted as C, germ, just means we're looking at a tiny neighborhood around the singularity ring.
You got it. And a monomial complete local ring describes the algebraic structure of the curve near that point.
Precisely.
Okay.
And these particular types of singularities are interesting because they have some unexpected connections to knot theory.
Interesting.
But we'll get to that later.
That's what keeps me coming back to the deep dive.
Oh.
Those surprising connections between seemingly disparate areas of math.
That's right.
Okay, so to really get a grip on the Motivic Hilbert Zeta function for these curved singularities, we need to understand something called the punctual Hilbert scheme.
Okay.
So for integers, the L1,
Right.
the punctual Hilbert scheme of CO is defined as C is an ideal of A with colength.
All right.
So it's the set of all ideals in the local ring of our curved singularity that have a specific colength.
Precisely.
Okay.
Now, one way to study this punctual Hilbert scheme is to embed it into a Grassmannian variety.
Ah, the Grassmannian.
Yeah, you remember that.
It's basically a space that parameterizes all the different subspaces of a given vector space
Exactly.
from linear algebra.
And there's this interesting result by Feaster and Steenbrink
Okay.
that defines a closed subset M of the Grassmannian that's closely related to our punctual Hilbert scheme.
So we're using this embedding to leverage the tools of linear algebra
Right.
to study the geometry of the punctual Hilbert scheme.
Right. And it gets even more interesting.
Even more interesting.
Yeah. When Eller is larger than a certain value, called the conductor of the semigroup, associated with the singularity.
All right.
The punctual Hilbert scheme coincides with something called the compactified Jacobian.
The compactified Jacobian.
Yeah.
It's essentially a way to extend the Jacobian variety to include points at infinity.
Exactly. But unfortunately, progress on explicit formulas for these compactified Jacobians has been slow.
So we need a different approach for our case.
Right. And that's where the stratification of the Hilbert scheme comes in.
Okay.
We can break down the Hilbert scheme into smaller pieces or strata based on certain properties of the ideals.
Right.
So we have this decomposition,
Yeah.
CU, where each C is a stratum corresponding to a particular subset of ideals.
Gotcha.
And to express the size or class of each stratum, we use the Grothendieck ring, which is essentially a way to do algebra with geometric objects.
So we're using algebra to study geometry.
It's a powerful approach.
It seems to be a recurring theme.
It is, and the key to computing the class of the punctual Hilbert scheme is to determine all the possible strata or subsemi-modules
Okay, subsemi-modules.
that can arise.
Now that's a term I need to brush up on.
It's related to the valuation semigroup of the singularity.
Okay.
Remember, the valuation semigroup is a set of numbers that describes the orders of vanishing of functions on the curve at the singularity.
Uh-huh.
A subsemi-module is essentially a subset of this valuation semigroup that satisfies certain algebraic properties.
So it's like a smaller fingerprint within the larger fingerprint of the singularity.
That's a great way to think about it.
Cool.
And to keep track of all these subsemi-modules, we can use a tree structure.
A tree.
Yes.
Like the ones with branches and leaves.
Yes. The vertices of the tree represent the different subsemi-modules.
Okay.
And the edges represent relationships between them, specifically the process of adding or deleting minimal generators.
Minimal generators. Those are like the building blocks of a subsemi-module.
Precise.
Yep. So by adding or deleting these building blocks, we can navigate through the tree and explore all the different subsemi-modules.
Precisely. And to make sure we don't miss any subsemi-modules, we use a special element called the Frobenius element.
The Frobenius element.
It's the largest element of the valuation semigroup that's not in a given subsemi-module.
Okay.
It helps us keep track of which subsemi-modules we can obtain by adding elements back in.
So the Frobenius element is like a guidepost helping us navigate the tree and ensuring we've explored all the possible subsemi-modules.
That's a great way to put it.
This is fascinating stuff.
It is, isn't it? And there's even more to uncover. For instance, the source material gives a concrete example of this tree structure for a singularity of type E6.
Okay.
It's a bit too complex to describe verbally, but you can see how this tree visually represents the relationships between the different subsemi-modules.
I'm looking at the diagram now, and even though it's intricate, I can see how each node and branch corresponds to specific subsemi-modules and their connections. This tree structure seems to be a powerful tool for understanding the punctual Hilbert scheme. But how exactly do we use it to compute the Motivic Hilbert Zeta function? That's a question I'm eager to explore further.
And that's exactly where we'll pick up in the next part of our deep dive.
All right, we're back and ready to delve deeper into this fascinating world of Motivic Hilbert Zeta functions. We left off talking about the tree structure associated with the valuation semigroup and how it helps us understand those subsemi-modules. But how do we bridge the gap between this abstract tree and the actual computation of the zeta function?
That's a great question, and this is where things get really interesting. The tree isn't just a way to organize the subsemi-modules, it actually encodes geometric information about the Hilbert scheme.
Okay, so each node represents a subsemi-module, which corresponds to a stratum in the Hilbert scheme.
Right.
But what about the edges? What do those represent?
The edges represent morphisms between strata in the Hilbert scheme. Specifically, each edge connects a stratum C to another stratum COAA, where mere is the subsemi-module you get by adding the Frobenius element back into U.
So moving along an edge in the tree corresponds to a specific geometric operation on the Hilbert scheme.
Exactly. And this morphism is a key ingredient in computing the class of each stratum in the Grothendieck ring.
Back to algebra again. So how does this morphism help us compute those classes?
The source material points out a key result. This morphism from C to C is a piecewise vibration.
Okay, piecewise vibration. I'm sensing a need for some unpacking here.
Essentially, it means we can break down the space into simpler pieces called fibers, each of which is mapped to a point in a base space. The piecewise part means that the fibers might look different over different parts of the base space.
So we're once again breaking down a complex object into smaller, more manageable pieces. It seems like a recurring theme in mathematics.
Absolutely, and this piecewise vibration gives us a fantastic tool, a formula to compute the class of C in terms of the class of C, and a certain power of the Lefschetz motive, denoted by L.
Lefschetz motive, is that like a mathematical driving force?
It's an important concept in algebraic geometry, but for our purposes, you can think of L as a special element in the Grothendieck ring. Think of it as a basic building block for classes of varieties.
Fair enough. So what's the formula that connects the classes of these strata?
Here it is, sachet Lesiocha. It might look a bit intimidating, but let's break it down piece by piece.
All right, let's unpack this. We have the classes of the two strata C and Cia, and then we have this L raised to a power. What's going on in that exponent?
The exponent is crucial. It's the difference between two quantities. The first HA counts the minimal generators of val that are smaller than the Frobenius element.
And the second quantity in the exponent.
The second quantity, CCHA, is a bit more subtle. It counts the minimal generators of the syzygy of A that are smaller than the Frobenius element and satisfy an additional condition denoted by CORS.
Hold on, CCG. I'm not familiar with that term.
The syzygy of A is another subsemi-module that describes the relations between the minimal generators of A. Think of it as capturing the dependencies between the building blocks of A.
Okay, so it's like a measure of how intertwined the minimal generators are. And this condition, COJ, what does that signify?
It basically means that we can combine the syzygy generator, say, with some minimal generator of A to get an element of the valuation semigroup that's bigger than the Frobenius element.
So we're being selective about which syzygy generators we count. They need to mesh with the Frobenius element in a specific way.
Precisely. Now, the source material gives some examples of how this formula works in practice. In example 2, they consider a simple singularity and show how to apply the formula to calculate the class of a particular stratum.
And in example 3, they highlight the importance of that condition on the syzygy generators.
Right.
It's not always trivial, and we need to be careful about which ones we count.
Right. These examples show that the formula, though complex, gives us a concrete way to calculate the classes of the strata, and by systematically working our way up the tree, applying this formula at each step, we can ultimately compute the class of the entire punctual Hilbert scheme.
So we're using the tree structure as a roadmap, and this formula as our compass, to navigate through the strata of the Hilbert scheme and eventually reach our destination, the class of the entire punctual Hilbert scheme.
That's a fantastic analogy. And once we have that class, we are tantalizingly close to the Motivic Hilbert Zeta function, but we need one more crucial piece, an algorithm to actually carry out these computations.
The practical implementation. So what does this algorithm look like?
The source material outlines a multi-step algorithm that takes as input the valuation semigroup of the singularity and its conductor.
And the output is the Motivic Hilbert Zeta function.
Exactly. Now, the algorithm itself is a bit too technical to delve into here, but the core idea is to use the tree structure and the formula we discussed to systematically compute the classes of the strata. It involves identifying minimal generators, computing syzygies, and applying that formula at each step.
So it's like a recipe with a tree, the strata, the syzygies, and the formula as our ingredients, and the algorithm as our instructions for combining them to create the Motivic Hilbert Zeta function.
That's a great way to think about it. And what's really cool is that the source material actually provides the Python code for this algorithm.
That's fantastic. But wait, there's something that's been bugging me. Remember how we said that the valuation semigroup is an infinite set? How can a computer deal with infinity?
That's a sharp observation. And it's a real challenge in implementing the algorithm. The solution is to truncate the valuation semigroup to a finite subset.
Truncate. So we're essentially chopping off the top of the tree. But how do we know where to make the cut? We don't want to lose essential information.
That's where the effective length of the valuation semigroup comes in. It's the smallest number, such that truncating the semigroup at that point still gives us the correct result for the zeta function.
So it's like finding the sweet spot. We want to truncate enough to make the computations feasible, but not so much that we sacrifice accuracy.
Exactly. And luckily, there's a theorem in the source material that gives us an upper bound for this effective length. It tells us that we can safely truncate at a point determined by the conductor and the smallest generator of the semigroup.
So we have a guarantee that if we truncate at this point, our algorithm will still produce the correct Motivic Hilbert Zeta function.
Precisely. This result is crucial for making the algorithm practical.
This is all starting to come together. But before we get too lost in the abstract, can we see an example of how this algorithm works in practice?
Absolutely. In section 7 of the source material, they apply the algorithm to a concrete singularity. They show how to determine the truncation point, compute the classes of the strata, and ultimately arrive at the Motivic Hilbert Zeta function.
I'm looking at their calculations now, and it's impressive how everything we've discussed, the tree, the vibration, the syzygies, the truncation, all come together to produce a tangible result. It's really satisfying to see it all work out.
It is quite elegant, isn't it? And this is just one example. The algorithm can be applied to a wide range of singularities.
This has been an amazing journey. We've covered so much ground. Hilbert schemes, valuation, semigroups, tree structures, syzygies, vibrations, truncation, and even a bit of Python code.
It's been a pleasure diving into these concepts with you.
But we're not quite done yet, right? We still haven't addressed that intriguing connection to knot theory. That's what I'm really excited to explore.
You're right. That's where we'll pick up in the final part of our deep dive.
All right, we're back for the final part of our deep dive into this Motivic Hilbert Zeta function for curved singularities. We've been on quite a journey, haven't we? Exploring Hilbert schemes, valuations, semigroups, even a bit of Python code. But there's one question that's been at the back of my mind. How does all this abstract algebra and geometry connect to something as tangible as a knot?
Well, that's the beauty of mathematics, isn't it? The most abstract concepts can have surprising connections to the real world.
I'm always amazed by that.
And it's true here, too. The Motivic Hilbert Zeta function for certain curved singularities is deeply connected to knot invariance.
Okay, knot invariance. There are those mathematical fingerprints for knots.
Right, exactly. Quantities that stay the same even when we deform a knot without cutting it.
Right.
They help us tell different types of knots apart and understand their properties.
Like whether two knots are really the same or how many crossings a knot has.
Exactly.
Right. I remember those diagrams from my topology days.
Yeah, so how does the Motivic Hilbert Zeta function, which seems to be all about abstract algebraic geometry, how does that enter the picture?
Yeah, good question.
It's all about finding the right bridge between these different worlds. The key is that certain knot invariants, like the famous HOMFLY polynomial, can be broken down into two parts.
Okay.
An algebraic part and a geometric part.
So we're separating the knot invariant into a more abstract part and a visual one.
Precisely. And it turns out that the algebraic part of these knot invariants is closely tied to the Motivic Hilbert Zeta function for certain curved singularities.
So they're kind of speaking the same mathematical language, even though they come from different areas of math.
Exactly. And this connection goes even deeper. Remember when we talked about embedding the punctual Hilbert scheme into a Grassmannian variety?
Yeah, that was pretty mind-bending.
Well, it turns out that some spaces associated with knots, like the knot conormal variety, can also be embedded into Grassmannians.
Wait, so we're seeing similar geometric structures in both knots and curved singularities?
Exactly. These shared structures allow mathematicians to move ideas back and forth between these two seemingly different areas.
Wow. So by studying the Motivic Hilbert Zeta function, we're not just exploring some abstract objects.
Right.
We're uncovering hidden connections to the real world.
Exactly. We're learning about the physical properties of knots.
This is incredible. So where do we go from here? What are the big open questions?
Well, one challenge is to develop more efficient algorithms to compute this Motivic Hilbert Zeta function. The one we talked about earlier is a good start, but it can get really computationally intensive for more complex singularities.
So we need to find some shortcuts without losing accuracy.
Precisely. Another exciting challenge is to understand the relationship between the Motivic Hilbert Zeta function and other knot invariants.
Right, we talked about the HOMFLY polynomial, but there are many others.
How do they all connect to the Motivic Hilbert Zeta function? What other connections are waiting to be found?
It sounds like we've only scratched the surface.
Oh, absolutely. There's so much more to explore.
Well, this has been an amazing deep dive. We've gone from abstract algebraic geometry to the concrete world of knots and seen how they're connected.
It's been a pleasure exploring this with you.
And to all of you listening, thank you for joining us on the deep dive. We hope you've enjoyed exploring this fascinating topic with us. We've only just begun to unravel the mysteries of the Motivic Hilbert Zeta function and its connection to knot theory. Who knows what other surprises await us as we delve deeper. Until next time, keep those mathematical minds engaged and curious. Welcome back to the deep dive. Today we're diving into, some pretty cutting-edge research in algebraic geometry. Specifically, we're focusing on a new algorithm for calculating the Motivic Hilbert Zeta function for curves with monomial singularities.
It's a pleasure to be here. This is a topic that's really at the forefront of the field.
It really is.
Blending, abstract algebra, geometry, and computational techniques in a fascinating way.
Right. So for our listeners who might not be as familiar with this area, let's start with a quick overview.
Yeah.
We're dealing with curves, which we can think of as one-dimensional objects defined by polynomial equations.
Okay.
And singularities are those points where the curve isn't smooth, like sharp cusps, or points where multiple branches intersect.
Right. And the Motivic Hilbert Zeta function is a way to capture intricate information about the geometry of these singularities. It's a refinement of the standard Motivic Zeta function, which, as you know, is already a pretty sophisticated object.
The paper we're looking at today, published in 2024, builds on some earlier work, including a 2020 paper, that proved the rationality of this Hilbert Zeta function for reduced curves.
Yeah,
So we know it can be expressed as a ratio of two polynomials,
exactly.
which is a good starting point.
Yes, that rationality result was a major step forward.
Yeah.
But actually computing this function, even knowing it's rational, is a whole other challenge.
And that's where this new algorithm comes in.
Exactly.
Can you give us a high-level overview
Sure.
of how it works? What are the key insights that make this approach possible?
The core idea is to exploit the structure of the punctual Hilbert scheme, which is a geometric object that parameterizes all the possible subschemes supported at the singularity. It's like a catalog of all the ways you can have a cluster of points concentrated at that singular point.
I remember from some earlier work by Feaster and Steenbrink that this Hilbert scheme can be embedded into a Grassmannian variety, which gives us some equations to work with.
Yeah.
But even with those equations, understanding the geometry of the Hilbert scheme remains a difficult task.
Exactly.
Yeah.
And that's why this new research is so significant.
Yeah.
They've found a way to break down the Hilbert scheme into smaller, more manageable pieces using the valuation semigroup of the curve singularity.
Yes, the valuation semigroup for curves with a monomial local ring, which is what this research focuses on.
Right.
This semigroup is generated by a finite set of integers.
Okay.
It captures information about the orders of vanishing a function
Exactly.
at the singularity.
Precisely. And the key insight is that you can stratify the Hilbert scheme by looking at the subsemi-modules of this valuation semigroup.
All right.
Each subscheme on the Hilbert scheme has its own valuation semigroup, which is a subsemi-module of the original one.
Got it.
So you group together all the subschemes with the same subsemi-module,
Right.
and that gives you a partition of the Hilbert scheme.
So we're essentially organizing the clusters on the Hilbert scheme based on their fingerprints, so to speak.
Exactly.
But how does that make the calculation of the Motivic Hilbert Zeta function any easier?
Here's where things get really interesting. The authors introduce a beautiful visual representation of these subsemi-modules as a tree structure. Each node on the tree corresponds to a subsemi-module.
Sure.
And the edges represent relationships between them.
A tree structure. That sounds surprisingly intuitive for such an abstract concept.
It is. And this tree is the key to the whole algorithm. Because it provides a systematic way to navigate the different strata of the Hilbert scheme. You can climb up and down the tree using certain operations.
I see.
And as you move along the branches, you can relate the motivic classes of the different strata. Using formulas derived in the paper.
Motivic class.
Yeah.
Can you remind us what that refers to in this context?
Of course. The motivic class of a variety is an element in the Grothendieck ring of varieties. It's a way to represent the variety in this abstract algebraic setting. So the goal is to compute the motivic class of the punctual Hilbert scheme. And this tree structure helps us break that calculation down into smaller, more tractable pieces.
I see. So we have this tree representing the different strata of the Hilbert scheme. And we can move around the tree and compute the motivic classes of the strata as we go.
Exactly.
But how do we actually get from those individual motivic classes to the motivic Hilbert Zeta function of the entire curve?
That's where the real ingenuity of the algorithm comes in. It involves a clever combination of those tree operations, the formulas for relating motivic classes, and a careful analysis of the minimal effective bound to ensure the computation is both accurate and feasible.
Gotcha.
But before we delve into those details...
Barbara, let's unpack those details. You mentioned this idea of a minimal effective bound. What is that exactly, and why is it so important for the algorithm?
It's a crucial aspect for ensuring the algorithm's practicality. Remember, the valuation semigroup is, in principle, infinite. But computers don't do well with infinity. So the algorithm works with a truncated version of the semigroup, considering only elements up to a certain bound.
So this minimal effective bound, which they denote as n in the paper, tells us how far we need to go out in the semigroup to guarantee that our calculations using the truncated version are still accurate.
Precisely. And determining this bound is non-trivial. We have a whole section devoted to this analysis. A key result is Theorem 3, where they establish a concrete upper bound for n based on two key properties of the semigroup, the conductor and the smallest generator.
Let me see if I'm following you. The conductor tells us when those ideals start behaving nicely. And the smallest generator is, well, the smallest element in the generating set of this semigroup.
Right, and this upper bound ensures that the computation remains feasible.
Yeah,
It's a delicate balance.
I see.
Truncate too much and you lose accuracy.
Sure.
Don't truncate enough and the computation becomes intractable.
So we've got this bound n, and we're working with the truncated semigroup now. Let's dive into the actual steps of the algorithm. You mentioned it relies on a few sub-algorithms, each with a specific role.
Absolutely. Think of it as a well-coordinated team.
Okay.
Algorithm 2 focuses on finding the minimal generators of a given sub-semi-module.
Okay.
Remember, each node on our tree represents a sub-semi-module, and this sub-algorithm identifies the essential elements within that sub-semi-module, the ones that can generate all others by adding elements from the original semigroup.
Okay, so it's finding the most efficient building blocks for each node on the tree. What about algorithm 3?
Algorithm 3 deals with something called the syzygy of a sub-semi-module. These syzygy elements capture relations between the generators. Remember that formula from Corollary 1 in the paper, the one that relates the Motivic classes of different strata.
Yeah.
The syzygy elements play a crucial role in that formula,
Right.
determining how the Motivic class changes as you move along an edge of the tree.
So we've got the building blocks from algorithm 2 and the relations from algorithm 3. Where does algorithm 4 fit in?
Algorithm 4 is the architect.
Okay.
It takes the truncated valuation semigroup as input and constructs the entire tree structure.
Right.
It systematically generates all the sub-semi-modules and the connections between them,
I see.
giving us that visual roadmap we talked about.
So it's like algorithm 4 builds the map, algorithm 2 provides the landmarks, and algorithm 3 figures out the directions between those landmarks.
Precisely. Now, algorithm 1 brings it all together.
Okay.
It initializes with the top node of the tree, which represents the full valuation semigroup -0,
Okay.
and then systematically explores the tree level by level.
So it's like a depth-first search exploring each branch of the tree.
Exactly. For each node, it calls upon algorithm 2 to find the minimal generators and algorithm 3 to compute the syzygy. Then it applies that key formula from Corollary 1 to relate the Motivic class of the current node to the Motivic class of its parent node.
It's like a recursive process working its way down the tree, using those formulas to piece everything together, and at the very end, it spits out the Motivic Hilbert Zeta function.
Precisely. Having calculated the Motivic classes of all these strata, algorithm 1 assembles them to obtain the final Motivic Hilbert Zeta function for the entire curve.
Right.
Remember, all of this is done with a truncated semigroup, and the bound n ensures that we're not losing crucial information in the process.
They even provide a detailed complexity analysis showing that the runtime of these algorithms is in fact manageable.
Right.
Thanks to the truncation and the efficient use of the tree structure.
Yes, the tree structure is what really makes this approach computationally feasible.
Yeah.
Without it, the number of computations would explode, making the problem intractable.
Now, I always love seeing these abstract ideas applied to a concrete example.
Right.
Did they provide a worked example in the paper?
They do. In Section 7, they walk us through the entire calculation for a specific curve singularity with a local ring defined by Zeta, ta. They illustrate each step of the algorithm, showing how the tree structure, the morphisms between strata and the bound on n are all used to arrive at the final result.
Excellent. I think that's a great place to pause. For now, we've covered a lot of ground, from the basic definitions to the intricate workings of the algorithm. But what I find most intriguing is what this new algorithm enables us to do. What are the broader implications of this research? Why should we care about being able to compute this Motivic Hilbert Zeta function?
That's a fantastic question, and it leads us to the heart of why this mathematical deep dive is so exciting.
So we've got this powerful new tool for calculating the Motivic Hilbert Zeta function. What doors does this open in terms of mathematical research?
One of the most promising avenues is the connection to knot invariance knot theory, as you know. Is a fascinating branch of topology, and there are deep and surprising links between knots and curved singularities.
It's always amazing to me how seemingly disparate areas of mathematics turn out to be connected in these intricate ways.
Exactly. And this algorithm could provide a new lens through which to study those connections.
Right.
By computing the Motivic Hilbert Zeta function for singularities associated with certain knots, we might gain new insights into the invariance of those knots.
The source material hints at ongoing research in this area. It sounds like there's a lot more to uncover.
Absolutely. And beyond knot theory, there are potential connections to other fields like representation theory.
Wow.
And even mathematical physics, the Motivic Hilbert Zeta function encodes a wealth of geometric information, and its applications might extend far beyond what we can currently imagine.
It's a reminder that even the most seemingly specialized mathematical tools can have far-reaching consequences.
Precisely. And this research also highlights the beautiful interplay between theoretical mathematics and computational methods, the need to truncate the valuation semigroup, and the careful analysis of the minimal effective bound showcase how practical computational considerations can drive theoretical insights.
It's a reminder that mathematics isn't just an abstract pursuit. It's also about finding creative solutions to problems and bridging the gap between theory and practice.
Indeed. And in this case, that bridge is built using a beautifully intuitive structure, a tree.
Yeah.
It's a testament to the elegance and power of mathematical thinking, even when dealing with highly abstract concepts.
I think we've done a fantastic job of deep diving into this research. We've explored the key concepts, the motivation behind the work, the intricate details of the algorithm, and even glimpsed its potential impact on other areas of mathematics.
It's been a pleasure discussing this with you. The authors of this paper have made a significant contribution to our understanding of curved singularities,
Yeah.
and I'm excited to see where their work leads in the future.
And to our listener, if you're eager to delve deeper into this topic, the authors have generously made their Python implementation of the algorithm publicly available. You can find the link in the source material.
It's a great opportunity to explore the algorithm firsthand and perhaps even contribute to this exciting area of research.
And as always, we're keen to hear from you. If you have any thoughts, questions, or suggestions for future deep dives, please don't hesitate to reach out.
Until then, keep exploring, keep questioning, and keep diving deep into the fascinating world of mathematics.
This is the Deep Dive signing off. Welcome back, everyone. We're diving into a really cool area of math today, one where algebra and geometry kind of like blend together. We're talking monomial curve singularities and their motivic Hilbert Zeta functions.
It's a fascinating area for sure. Lots of elegant connections you'll see. And yeah, we'll be focusing on those curves with monomial local rings, the ones that look like Zeta 1, Zeta.
And our listeners are definitely familiar with the Hilbert scheme of points, I'm sure, and how important it is for understanding these singularities. But what's really exciting about this deep dive is that we're going to try and find an algorithm to actually compute the motivic Hilbert Zeta function. It's written as ZAQ, right, for these types of curves.
You got it. This function, it's a series, really, with coefficients that come from the Grothendieck ring of varieties over C. It's packed with geometric information about our singularity. And to come up with an algorithm for computing it, well, you need some clever combinations of combinatorial and geometric ideas.
Okay, I'm following so far. So we've got this specific type of curve singularity, the ones with monomial complete local rings. What is it about this structure that's so interesting when we're thinking about the Hilbert scheme?
Well, the Hilbert scheme, think of it as like a catalog. It lists out all the possible subschemes of a given space. And in this case, it's our singular curve that we're interested in. So by really getting a handle on the structure of the Hilbert scheme, we can learn a lot about the singularity itself.
So the Hilbert scheme is kind of like a tool or a lens that we can use to look deeper into the singularity and all its complexities.
That's a great way to put it. It's like we're zooming in on all the intricate details. And to zoom in even further, we'll focus on the punctual Hilbert scheme. It's denoted as C, and it sort of narrows our view to those subschemes that are all bunched up at a single point. It gives us a really localized perspective on how the singularity behaves.
But I imagine actually trying to picture C directly in your head must be pretty tough, right? It's not exactly an easy thing to visualize.
Oh, you're absolutely right about that. The structure of C can be a real tangled mess, which is why we need a good strategy to tackle it. That's where stratification comes in. We break down this complex object into smaller, more manageable pieces.
Stratification. Okay, that sounds like a pretty powerful tool.
Yeah.
How does that work exactly when we're dealing with the punctual Hilbert scheme?
So we divide up C into separate pieces, like cutting a cake, and each piece is defined by something called a subsemimodule, denoted as Te, and that gives us this equation. Each piece, each stratum, is represented by C and corresponds to a particular A subsemimodule.
So it's like each subsemimodule defines a unique stratum, a piece of the puzzle. And if we can understand these individual pieces, we can start to see the bigger picture of the punctual Hilbert scheme.
Exactly. It's like assembling a jigsaw puzzle, piece by piece, until we reveal the intricate structure of CA.
Okay, now to understand these subsemi-modules, we need to talk about something called the valuation semigroup, denoted as OI. It's basically a set of numbers, right? And it encodes all this important information about the singularity.
Precisely. It captures how powers of the parameter 2 show up in the local ring of the singularity. You can think of it like a fingerprint that uniquely identifies our singularity.
Hmm. Very cool. So how do these subsemi-modules relate to the valuation semigroup?
Think of them as special subsets of the valuation semigroup. They're closed under addition, meaning if you take an element from the subsemi module and add an element from a calo, you get another element that's still in the subsemi module. And these subsemi modules, they actually match up with ideals in the local ring of the singularity. So we're creating this link between algebra and geometry, connecting ideals and subsemi module.
So we're bridging these two worlds, the algebraic world of ideals and the geometric world of subsemi-modules. It's like there's this hidden correspondence between them.
Exactly. And to bring some order to all of this, we use the valuation semigroup to create a tree structure, which we denote as Go. And a key player in this construction is something called the Frobenius element, denoted as O.
Frobenius element. Okay, what role does this Frobenius element play in building this tree?
So the Frobenius element is the biggest element that isn't part of the subsemi module. If we add this element back to O, we get a new subsemi module. And by adding and removing this Frobenius element, we can link different subsemi modules together, forming the branches of our tree.
So it's like the Frobenius element acts as a bridge between different levels of the tree, connecting different subsemi modules together.
That's a perfect way to think about it. To see how this works in practice, let's look at a simple example. They use A equal K3 T4 in the source. The valuation semigroup here is AA3 for Ho, which is all the numbers you can get by adding multiples of 3 and 4, starting with 0. So it's like 0, 3, 4, 6, 7, 8, 9. And the conductor, denoted as C, is 6.
So we start with the semi-module 3, 4, which is basically all the elements in AO except for 0.
Right. And then we use what we call deletion maps, denoted as DO. These maps create new subsemi modules by taking out specific generators. So for example, if we apply D11 to 3, 4, we get 4, 6, 7, 8, 9, which is minimally generated by 4, 6. And if we apply D012 to 3, 4, we get 3, 6, 7, 8, 9, AE. So we're branching out, creating new subsemi modules by removing certain generators. But where does the Frobenius element come into all of this?
Each time we remove a generator, we can figure out what the Frobenius element is for the new subsemi module. So for 4, 6, the Frobenius element is 5 because it's the largest element in D that's not in 4, 6. If we add 5 back to 4, 6, we get our original semi-module 3, 4.
So the Frobenius element lets us move back up the tree, connecting different levels of subsemi modules.
Precisely. We just keep repeating this process, deleting generators and finding the Frobenius element to build our tree structure, Go. The vertices represent different subsemi modules, and the edges represent the connections between them, all guided by the Frobenius element. This tree structure is really quite elegant. It's like a map through this whole intricate world of subsemi modules, connecting them in a beautifully organized way.
It really is, isn't it? And this map is going to lead us to even more exciting mathematical territory, piecewise fibrations. These fibrations show us deeper geometric connections between different strata of the Hilbert scheme. But before we jump into that, let's take a moment to appreciate the structure we've uncovered so far. We've explored curved singularities, the punctual Hilbert scheme, the valuation semigroup, and this amazing tree built from Adzefin subsemi modules.
It's incredible how all these abstract ideas come together to give us a clearer picture of how a singularity is structured. And I'm really curious to see how these piecewise fibrations add even more depth to our understanding.
I think you'll find it very illuminating, but we'll have to save that for next time.
All right, so we've spent some time building this intricate tree structure. We use the valuation semigroup and the Frobenius element. And you mentioned this leads to something called piecewise fibrations. Can you remind me what these fibrations are exactly? And how do they relate to the geometry of the Hilbert scheme?
Sure. Piecewise fibrations, think of them as a way to capture the geometric relationships between the different strata of the Hilbert scheme. It's like each stratum is a piece of fabric, and a piecewise fibration describes how those pieces are sewn together, showing us the connections between them.
Okay, I can kind of picture that. So how does this sewing together relate back to our tree Go and the concept of subsemi modules?
The edges in our tree, those actually represent geometric morphisms between those strata associated with the connected vertices. And each morphism, it captures the connection between the classes of these strata, in the Grothendieck ring, of course.
Ah, the Grothendieck ring.
Yeah.
Right, that's where we work with classes of varieties. So these vibrations actually tell us something about how those classes are related.
Exactly. And there's a key insight into this relationship. It's in Theorem 1 in the source material. This theorem, along with Corollary 1, gives us a formula to actually calculate the class of C in the Grothendieck ring.
That sounds incredibly useful. Can you walk me through how this formula works? It mentions something called a syzygy, right? What's a syzygy in this context?
A syzygy, it's another subsemi-module, and it's written as syzygy. Basically, it describes relations between the minimal generators of C. You can think of it as capturing the dependencies between those generators.
Interesting. So we've got our subsemi module Yizi, its syzygy, and tia. How do these all fit together in the formula for the class of C?
The formula tells us that C equals times L raised to a certain power. That power is the number of generators of C that are less than A minus the number of generators of C that are less than A and satisfy an additional condition. That condition is denoted as C, and it ensures that there's some generator of S such that C plus ski belongs to A.
So it's like we're picking out specific elements from A and Cis based on how they relate to the Frobenius element. And that information helps us connect the classes of C and C.
Precisely. It's a beautiful interplay between the structure of these subsemi modules and the geometry of the strata. To make this more concrete, let's look at an example. Example 2 from the source material is a good one.
I always appreciate a good example.
So they use a curve defined by y4 equals by 7. The valuation semigroup here is A for 7. Let's say our subsemi module is 8, 11. So it includes all the elements generated by 8 and 11, and we can add elements of A as well.
All right, so what's the Frobenius element for this particular check?
In this case, the Frobenius element cus is 21. It's the largest element in E that isn't in A. Now we need to figure out the syzygy, Cis, which for this example is 1532.
We have A, Cis, and gave. So how do we use the formula to find C811?
First, we look for generators of A that are strictly less than S. So we have 8 and 11, those are 2.
And then we need to look at the generators of Cis, which are 15 and 32.
Mm-hmm.
But we only care about the ones that are less than Cis and also meet that Saigon condition.
Right. Only 15 fits both of those. It's less than 21. And 21 minus 15 plus 8, that equals 14, which is an A.
Okay, so if I'm following the formula correctly, C811 should equal C81121 multiplied by L.
You got it. That's exactly how the formula captures the relationship between these two strata in the Grothendieck ring. It shows how we connect the combinatorial stuff with the subsemi modules and the geometric information with the classes of strata.
This is really fascinating, but it seems like this formula relies on already knowing the class of Cis. How do we actually compute that?
That's a great question. And it leads us to the heart of the algorithm for calculating the Motivic Hilbert Zeta function. This algorithm uses the tree structure we built, working its way through all the strata, applying this formula to calculate the class of each one.
Okay, I'm ready to dive into this algorithm. But first, can you remind me how this algorithm relates to the Motivic Hilbert Zeta function, the one we talked about at the beginning?
Of course. Remember, we're ultimately trying to compute Z-Hild, CRQ, which is that generating function that encodes information about the punctual Hilbert scheme for all values of Asian. The classes of those strata, the CA, they're the building blocks of this function. Once we have a way to calculate those classes efficiently, we can put them all together to get the Motivic Hilbert Zeta function.
Ah, so the algorithm gives us the pieces, and then we assemble those pieces to get the full picture represented by the Motivic Hilbert Zeta function.
Exactly. Now, the algorithm itself is pretty clever, but it has a challenge to overcome. The valuation semigroup, it's an infinite set.
Right. Infinity can be a bit tricky when we're dealing with computers. How does the algorithm deal with this infinity issue?
It uses a strategy called truncation. Instead of dealing with the whole semigroup, we just focus on a finite part of it, denoted as A. It includes all the elements of a point up to a chosen bound line.
That makes sense.
Yeah.
But how do we pick the right N? How do we make sure it's big enough to get accurate results?
That's where we introduce the minimal effective bound, which is N, and the minimal effective length, which is N. N is the smallest N that will guarantee the algorithm works correctly, and N is the number of elements in that truncated set, NN.
So finding N is super important for the algorithm to work properly.
Mm-hmm.
How do we determine that bound?
Theorem 3 in the source material, it gives us a really useful upper bound for n. It says that n is less than or equal to C1 times R1 plus 2, where C is the conductor of n and O1 is the first generator of n.
So we have a way to make sure we're truncating correctly.
Awesome. Now let's get into that algorithm itself.
Algorithm 1, that's what they call in the source. It starts with the initial stratum, C1, which corresponds to the whole semigroup except for 0. And then it uses algorithm 4 to generate all the other strata, which essentially builds our tree gay. Algorithm 4 is our tree-building subroutine, right? And what happens next?
Algorithm 1 then goes through each stratum and calculates its class using that formula we were discussing earlier. For each stratum, it first figures out the Frobenius element and uses algorithm 3 to find the syzygy, syzes.
Those are the essential ingredients for our formula. And algorithm 2 also comes into play, doesn't it?
Absolutely. We use algorithms 2 and 3 to find the minimal generators of both ev and syzes. Those are the generators that we need to carefully count for the exponent of L in our formula.
Okay, so we have algorithm 2 finding those minimal generators, algorithm 3 finding syzygies, and algorithm 1 managing the whole process, using the formula to calculate the class of each stratum. It's like an intricate dance of algorithms working together.
A perfectly choreographed mathematical dance. By breaking down this complex task into smaller, well-defined steps, the algorithm gives us an efficient and elegant way to compute the Motivic Hilbert Zeta function.
Okay, so we've covered all the theory. We went deep into the valuation semigroup, subsemi modules, and that super cool formula that connects their classes in the grothendec ring. But theory is only one side of the coin. I'm really excited to see this algorithm actually working.
Me too, actually. You know, it's those concrete examples where the beauty of math really shines. The source material has a great example, example 4, I think. They use a curved singularity with a local ring of C4, T5, T6. So the valuation semigroup is OS4, 5, 6, and the conductor is C8.
Okay, so if we use theorem 3, we can figure out an upper bound for n, that truncation point for our semigroup. They set n to be 8 to 1, 4 plus 2, which is 42. So we're going to be working with that truncated semigroup O42.
Right. Now, the first step is to generate all the different strata we need. They use algorithm 4 for this, and it gives them sets labeled D1, D2, and so on up to D8. Each set has the subsemi-modules that match a specific level in our tree, G.
Right, that's our tree-building subroutine doing its thing. And once we've got all the strata, then the real fun begins. We get to calculate the class of each one.
Exactly. They use algorithm 1 to carefully go through each stratum and calculate its class using that formula we talked about earlier. It figures out the Frobenius element, GOSI, and the syzygy, Sayur, for each subsemi-module, and then it meticulously counts the right generators to get the exponent of L in that formula.
And if we do this for each stratum, step by step, we'll end up with the Motivic Hilbert Zeta function for this specific curved singularity. It really is like solving a puzzle, putting all the pieces together until we can see the full picture.
I like that analogy, and what's really neat is that they actually check to make sure that N8042 actually satisfies the condition from Theorem 3. It confirms that all their tabulations are good. It's really that attention to detail that guarantees we get an accurate result.
It's so cool to see how this theoretical framework becomes a concrete algorithm that we can actually use. It really shows just how powerful algorithmic thinking is in mathematics.
Absolutely. By breaking a big, complicated problem into smaller steps, we can create powerful tools to explore and understand all sorts of intricate mathematical structures.
We've covered so much ground in this deep dive. We explored curved singularities, dug into the structure of the punctual Hilbert scheme, and uncovered some of the secrets hiding within the valuation semigroup.
And we even got to touch on these elegant ideas like piecewise fibrations and see how algorithms can help us unravel these complex mathematical structures.
And I'm sure I'm not alone in being left with even more questions. Could we use similar methods with other types of singularities? What are the broader implications of this algorithm? Does it connect to other parts of mathematics? I'm sure there's a lot more to explore.
Those are great questions. You know, the world of math is full of these amazing connections. Maybe this algorithm can shed some light on knot invariants, especially with those connections to the Hamfly polynomial. Or maybe it can even give us new insights into moduli spaces. Who knows what we might find? The possibilities are really endless.
That's what makes it so exciting. There's always something new to discover. I want to give a huge thank you to our amazing expert speaker for guiding us through this intricate mathematical landscape. I really appreciate it.
The pleasure was mine, truly. I always love sharing the beauty and wonder of mathematics.
And of course, a big thanks to all of our listeners for joining us on this deep dive into the world of monomial curve singularities and the Motivic Hilbert Zeta function. Until next time, keep exploring, keep wondering, and keep discovering all the incredible things that mathematics has to offer. Wow, you've given us some pretty intense source material for this deep dive.
Oh, yeah.
We're tackling some serious algebraic geometry this time,
Yeah.
exploring the Motivic Hilbert Zeta function and how it relates to curve singularities.
Yeah.
Not exactly light reading, but I think we can break it down.
Yeah, absolutely.
So for those who maybe aren't familiar with this particular area of math, can you explain what the Motivic Hilbert Zeta function is?
Right. So the Motivic Hilbert Zeta function is a really powerful tool in algebraic geometry.
Okay.
It gives us a lot of detailed information about geometric objects, specifically a variety. So you can think of a variety as being a set of points that are defined by some polynomial equations.
Okay.
And these varieties can have parts that are smooth, and then they can also have parts that are singular.
Okay.
So those are the singularities that we're talking about.
Got it. So is that what makes it different from the regular Motivic Zeta function?
That's exactly right.
Okay.
So the regular Motivic Zeta function, it kind of treats every variety as if it were smooth.
Okay.
And it can't really see these singularities. The Hilbert Zeta function is a little bit more refined.
So it gives us a better picture of what's happening
Exactly.
at these singularities.
Exactly. It's
Yeah.
more refined and invariant.
I like that. So we're basically getting like a super high resolution picture
Yeah, exactly.
versus just like a blurry X-ray.
That's a great way to put it.
And I know for this deep dive, we're focusing specifically on the Motivic Hilbert Zeta function for curves
Right?
with monomial local rings.
Right.
Can you explain why the focus on curves and what those are?
Yeah, so curves are sort of like the building blocks of algebraic geometry.
Okay.
And in a lot of ways, they're much simpler to work with than higher dimensional objects, but they can still exhibit a lot of interesting behavior.
Okay.
And especially when you start talking about singularities.
Okay.
And then these monomial local rings, they basically just describe the algebraic structure around those singularities.
Good.
So they give us a language to use when we want to analyze those points.
Okay. And I know your source material goes into an algorithm for actually calculating this,
Right.
which sounds very complicated.
Yeah, yeah. And the reason why it's so complicated is because we're dealing with sets that are infinite.
Right.
And so in order for us to actually be able to compute anything, we have to be a little bit clever and find ways of like truncating these sets.
We're not literally just chopping them off.
Right. Yeah. It's more like we're
Yeah.
choosing a specific piece of it that's finite,
Okay.
but in a way that preserves all the important information.
So it's almost like taking a core sample
Exactly.
of like a massive glacier or something.
Exactly. Yeah.
And then from that core sample, we can extrapolate out
Right.
what the rest of it looks like.
Yeah. That's a great analogy.
So what are some of the key steps that are involved in this truncation?
Right. So the first step is that we have this this infinite valuation semigroup, which we denote by the Greek letter gamma, and we need to truncate that to a finite subset.
Okay.
And basically what this valuation semigroup does is it encodes the orders of vanishing of functions at the singularity.
Okay.
And then once we've truncated the semigroup, the next step is we use a tree,
Okay.
which is denoted by G of gamma, to represent all of the possible subsemi-modules of gamma.
Okay.
And so each one of these subsemi-modules actually corresponds to like a different stratum in the Hilbert scheme. So this tree is sort of giving us a roadmap
Okay.
to navigate all of the different strata.
I like that. It's like our little guide through this
Exactly.
Hilbert scheme.
Exactly.
And then from there, we're applying a piecewise fibration
Right.
to relate those classes of the strata in the grothendieck ring.
Right. So this grothendieck ring allows us to work with these geometric objects in a way that's algebraic.
Okay.
And then this piecewise fibration just tells us how to connect the motivic information between these different strata.
So it's a multi-step process. Very intricate.
It is, yeah.
But you said there's a particular detail in the source material that caught your eye.
Right.
Can you tell me more about that?
Yeah, so in corollary 1, there's this condition
Okay.
that says sigma sub I has to be less than gamma.
Okay.
And this condition isn't always trivial.
So what does that mean? What is a syzygy?
Right, so a syzygy is basically just a relation between the generators of a module.
Okay.
So for example, if you have...
So it tells us the rules for combining those generators.
Exactly. Yeah.
And then this condition determines which of those are relevant.
Exactly.
Sound.
So it tells us which ones contribute to the Motivic class.
Okay, and why is this condition so tricky? Why is it not obvious?
Right, so sometimes it's very clear whether or not this condition is satisfied.
Okay.
But in other cases, it might require a little bit more analysis.
So let's look at an example to illustrate this.
Yeah, so in example 3 in your source material, we're looking at this local ring, C double brackets, T to the 4th, T to the 6th, T to the 13th double brackets.
Okay.
And that gives us the semigroup. Gamma equals 4, 6, 13.
Okay.
And so we're looking at this subsemi-module delta, which is generated by 4 and 6.
Okay.
And so the syzygy of this subsemi-module is 10, 12. And the Frobenius element, gamma sub delta, is 13.
Okay.
So the question is there a way to combine...
Yeah, 13 with the 4 and 6 to get either 10 or 12.
Exactly.
And in this case, it looks like no.
In this case, no.
So the condition isn't met.
Right.
What does that mean?
So that means that neither of the syzygies, 10 or 12, actually contribute to the Motivic class.
Okay, so it simplifies our calculation.
Exactly.
And so I know to solidify this, we're going to walk through the calculation of the Motivic Hilbert Zeta function for a specific curve singularity.
Right.
Which one are we tackling?
So let's look at the curve singularity that has the local ring C, double brackets, T to the 4th, T to the 5th, T to the 6th, double brackets.
Okay, so first things first, what's the semigroup for this curve?
Okay, so the semigroup is generated by those exponents, so 4, 5, 6.
Right.
And we denote that by gamma, so gamma equals generated by 4, 5, 6.
So then what's the next step in applying this algorithm?
Okay, so the next step is we need to truncate this semigroup.
Okay.
And according to theorem 3, the minimum bound that we need to use is C minus 1 times alpha 1 plus 2.
And what are those?
Where C is the conductor,
okay,
and alpha 1 is the smallest generator.
Okay, and what are those in this example?
So in this example, C is 8, and you can think of the conductor as being the point after which every integer belongs to the semigroup.
Got it.
And then alpha 1 is just 4.
Okay.
So if you plug those into the formula, you get 42.
Okay, so we're working with the truncated semigroup gamma greater than or equal to 42.
Exactly.
Okay, and what do we do with this?
So then we need to figure out what these sets, D1, D2, all the way up to D sub C look like.
Okay.
And each one of these sets is going to contain subsemi-modules of this truncated semigroup.
Got it.
And then we use the algorithm to systematically generate those sets.
So what does D2 look like?
Okay, so D2 consists of these 3 subsemi-modules.
Okay.
5, 6, 8, 4, 6, and then 4, 5.
Okay.
And each one of those is actually obtained by removing a generator from the subsemi module that's in D1, which is just 4, 5, 6.
Got it. So we're systematically exploring all the possible combinations.
Exactly.
By removing those generators.
Right.
What about D3?
So D3 is going to be 6, 8, 9, 5, 8, 5, 6, and then 4, 11.
And so we're just building this out until we get to D8.
Exactly.
Okay, and how do we use these to actually calculate the Motivic Hilbert Zeta function?
So that's where corollary 1 comes in.
Right.
So for each subsemi-module that's in each one of those sets,
okay,
we apply corollary 1 to figure out what the Motivic class is.
Got it.
Got it. And so we need to determine what the Frobenius element is, what the syzygy is, and check if that condition sigma sub I by less than gamma is satisfied.
Okay.
And then once we have all those Motivic classes,
okay,
then what we do is we sum them up at each level.
Okay.
And that's going to give us the coefficient for Q to the L,
okay,
where L is the level.
Got it. So we're building out this power series.
Exactly.
Okay. Well, I think that's a good place to take a break.
Okay.
And then when we come back, we'll actually look at calculating those Motivic classes.
Sounds good. Welcome back. Hopefully that was enough time to process all that.
Yeah, definitely a lot of information.
It is, yeah.
But I think I'm ready to dive into actually calculating those Motivic classes.
Okay, great.
So do you have a good example that we can start with?
Yeah, so why don't we start with the subsemi-module delta equals 8 from D8.
Okay, so this is the subsemi-module generated by the single element 8.
Right.
How do we figure out the Motivic class?
Okay, so we're going to use corollary 1. And that tells us that C bracket delta bracket equals C bracket M of delta bracket times L to the cardinality of gamma sub I, such that gamma sub I is less than gamma sub delta minus the cardinality of sigma sub I. such that sigma sub I is less than gamma sub delta, and sigma sub I is less than gamma sub delta. So let's break this down.
Yeah.
So first, we need to find what the Frobenius element is for 8.
Right, so that's the largest element, our truncated semigroup, gamma greater than or equal to 42. That's not in our subsemi-module.
Right.
So wouldn't that be 15?
Yes, exactly.
Right.
And then what about the syzygy for this subsemi-module?
So the syzygy represents the relations between the generators of the subsemi-module.
Right.
And since there's only one generator, 8, there wouldn't be any relations.
Exactly, yeah.
So the syzygy is empty.
The syzygy is empty in this case.
Okay.
And so because of that, the condition that sigma sub I has to be less than gamma is automatically satisfied.
Okay, it's like it's not even applicable in this case.
Exactly, yeah. So now if we go back to corollary 1, we need to figure out what m of delta is.
Okay.
And so m of delta is just going to be the union of delta and its Frobenius element.
Okay, so in this case, that would be 8, 15.
Yes, exactly.
Yeah. Okay.
And then we also need to figure out what these exponents are.
Okay.
So cardinality of gamma sub I, where gamma sub I is less than gamma sub delta. And then cardinality of sigma sub I, where sigma sub I is less than gamma sub delta, and sigma sub I is less than gamma sub delta.
Okay.
So the first one, cardinality of gamma sub I such that gamma sub I is less than gamma sub delta. That represents the number of generators in delta that are strictly less than gamma sub delta.
Okay.
And so we only have one generator, 8.
Right.
And that's less than 15.
So that's 1.
So that's 1.
Okay.
And then for the second cardinality, that's the number of elements in the syzygy that are both less than gamma sub delta and that satisfy the condition that sigma sub I is less than gamma sub delta.
And since our syzygy is empty,
Right.
that would be 0.
That's going to be 0.
Okay, so putting all of that together.
Right. So if we put all of that together, we get that C bracket 8 bracket equals C bracket 8, 15 bracket times L to the 1 minus 0.
Okay.
So we can simplify that as C bracket 8 bracket equals C bracket 8, 15 bracket times L.
So we've basically expressed the Motivic class in terms of the Motivic class of the flirter.
Yep. Okay, cool.
So we've kind of taken our first step there.
Yeah.
Are you ready to move on to a slightly more complicated example?
Let's do it. I'm starting to get the hang of this a little.
Okay, cool.
Let's try 4, 5 from D2.
Okay, so in that case, delta is 4, 5.
Okay.
The Frobenius element, gamma sub delta, is going to be 13.
13, okay.
And then the syzygy is generated by 9 because 9 is 4 plus 5.
Right, okay.
So now we need to check and see if this condition, sigma sub I is less than gamma, is satisfied.
So our sigma sub I is 9. And we need to see if there's a generator in 4, 5 that when added to 13 minus 9 gives us an element in our truncated semigroup. Right.
And it looks like it does.
It does.
If we take 5, 13 minus 9 plus 5 is 9, which is in that truncated semigroup.
Exactly. Yep.
Okay, so it's satisfied.
So the condition is satisfied.
Now, how do we apply corollary 1?
Okay, so m of delta is going to be 4, 5, 13.
Okay.
And then that first cardinality of gamma sub I, where gamma sub I is less than gamma sub delta, that's going to be 2.
2, because both 4 and 5 are less than 13.
Exactly.
Okay.
And then the second cardinality is going to be 1, because that syzygy element 9 is less than 13, and it satisfies the condition.
Okay, so plugging all of that in?
So if we plug all that in, we get that C bracket 4, 5 bracket equals C bracket 4, 5, 13 bracket times L to the 2 minus 1.
Which we can simplify as C bracket 4, 5 bracket equals C bracket 4, 5, 13 bracket times L.
Right.
Okay.
So again, we've expressed the Motivic class of one stratum in terms of another stratum.
Okay, cool. So we're systematically working through all of these, building upon the ones that we've already done.
Exactly, yeah.
But I do have a question.
Okay.
In both of these examples, we've encountered syzygies that only have one generator.
Right.
Is it possible for them to have multiple generators?
Yes, absolutely. As you start looking at subsemi modules that are more and more complicated, a lot of times they'll have syzygies that have more generators.
So we might have more to check.
You might have more to check,
Yep.
but the process is still the same.
Yeah.
You just have to apply corollary 1 and check that condition for every element of the syzygy.
But before we calculate all of the Motivic classes for our example, I think it's important to zoom out for a minute
Okay.
and talk about why are we doing this?
Right.
What is the point of calculating the Motivic Hilbert Zeta function?
So it's not just about like numbers and formulas.
Right.
The Motivic Hilbert Zeta function really gives us a lot of information about the geometry of these curves and these singularities.
Okay.
So for example, it gives us a way to classify different types of singularities.
So two singularities with different Motivic Hilbert zeta functions will have distinct geometric properties.
Exactly.
Cool. So we're really uncovering like the underlying secrets of these algebraic structures.
Yeah, and this algorithm that we've been talking about gives us a way to do that that's really systematic and rigorous.
Yeah.
So it's really quite beautiful how this all works.
Okay, well now I'm even more excited to actually calculate this Motivic Hilbert zeta function and see what it tells us.
Okay, great.
But I think that this is a good place to stop for now.
Okay.
Let our listeners digest this, and then we'll come back and do those final calculations.
Sounds good.
Okay, so I'm ready to see this all come together.
Yeah.
We've explored the Motivic Hilbert zeta function. We've used that tree structure to navigate the Hilbert scheme.
Mm-hmm.
We've wrestled with L's and G's.
Yeah.
It's time to put it all together and actually calculate the Motivic Hilbert zeta function for this curved singularity. So for our example, with local ring C, double brackets, t to the fourth, t to the fifth, t to the sixth, double brackets. Let's start with level 1,
Okay.
which is D1.
Okay.
We only have one subsemi module there.
Right.
4, 5, 6. What's its Motivic class?
Yeah, so that's actually the easiest one.
Okay.
Because C bracket 4, 5, 6 bracket, that represents the entire punctual Hilbert scheme.
Okay.
And so its Motivic class is just 1.
It's like the base case.
Exactly. Yeah.
Okay, so what about level 2, which is D2?
Okay, so for D2, we have these 3 subsema modules.
Okay.
5, 6, 8, 4, 6, and 4, 5.
Mm-hmm.
And if we apply corollary 1 and go through all the calculations, we find that each one of them actually has Motivic class L.
Oh, so they're all the same.
They're all the same.
Is that a coincidence?
It's not necessarily a coincidence. It just kind of means that even though these subsemi modules have different generators,
Yeah.
they all kind of have similar geometric properties.
Interesting. Okay.
Yeah.
So what about D3?
Okay, so for D3, things start to get a little bit more diverse.
Go ahead.
So we have 4 subsemi modules,
Okay.
and the Motivic classes are C bracket 6, 8, 9 bracket equals L squared,
Okay.
C bracket 5, 8 bracket equals L squared,
Okay.
C bracket 5, 6 bracket equals L squared,
Okay.
and then C bracket 4, 11 bracket equals L.
So they're not all the same anymore.
Not all the same anymore.
Okay.
Yeah, and that kind of makes sense because as we're moving further down this tree,
Right.
the stratas are getting more and more complicated.
All complex, yes.
And so that's reflected in these Motivic classes.
Right. So not just telling us the number of strata, but like you said, their complexity.
Exactly. Yeah.
Cool. So do you have the results for the rest of the levels?
I do.
Or do we need to calculate them all out?
Yeah, why don't I just give you those so we can
Right
get
then.
to the final result.
Okay.
Okay, so for D4, we have C bracket 8, 9, 10, 11 bracket equals L cubed. C bracket 6, 9 bracket equals L squared. C bracket 6, 8 bracket equals L squared.
Mhm.
C bracket 5, 12 bracket equals L squared.
Okay.
And then C bracket 4 bracket equals 1.
Okay.
For D5, we have C bracket 9, 10, 11, 12 bracket equals L cubed.
Okay.
C bracket 8, 10, 11 bracket equals L cubed. C bracket 8, 9, 11 bracket equals L cubed. C bracket 8, 9, 10 bracket equals L cubed.
Okay.
C bracket 6, 13 bracket equals L, and then C bracket 5 bracket equals 1.
Okay.
For D6, we have C bracket 10, 11, 12, 13 bracket equals L to the 4th.
Yeah.
C bracket 9, 11, 12 bracket equals L cubed. C bracket 9, 10, 11 bracket equals L cubed. C bracket 9, 10, 11 bracket equals L cubed. C bracket 8, 11 bracket equals L squared. C bracket 8, 10 bracket equals L squared.
Okay.
C bracket 8, 9 bracket equals L squared, and then C bracket 6 bracket equals 1.
Okay.
For D7, we have C bracket 11, 12, 13, 14 bracket equals L to the 4th. C bracket 10, 12, 13 bracket equals L cubed. C bracket 10, 11, 13 bracket equals L cubed. C bracket 10, 11, 12 bracket equals L cubed. C bracket 9, 12 bracket equals L squared. C bracket 9, 11 bracket equals L squared.
Okay.
C bracket 9, 10 bracket equals L squared. And then C bracket 8, 15 bracket equals L.
Okay.
And then lastly, for D8, we have C bracket 12, 13, 14, 15 bracket equals L to the 4th. C bracket 11, 13, 14 bracket equals L cubed. C bracket 11, 12, 14 bracket equals L cubed.
All right.
C bracket 11, 12, 13 bracket equals L cubed. C bracket 10, 13 bracket equals L squared. C bracket 10, 12 bracket equals L squared.
Right.
C bracket 10, 11 bracket equals L squared. C bracket 9, 16 bracket equals L.
Okay.
And then C bracket 8 bracket equals 1.
Okay. So we have all of our Motivic classes.
We do.
Let's put it all together and get that final expression for the Motivic Hilbert zeta function.
Okay, so what we're going to do is for each level, we're going to add up all the Motivic classes, and then we're going to multiply by the appropriate power of Q.
Okay.
So for level 1, it's just going to be 1 times q to the 1.
Okay.
For level 2, it's going to be L plus L times q squared, which we can simplify as 3LQ squared.
Got it. Okay.
And so on.
Okay.
And so if we put all of that together, the Motivic Hilbert Zeta function for this curved singularity with local ring C double brackets t to the 4th, t to the 5th, t to the 6th double brackets is z sub Hilb open parenthesis c comma o close parenthesis open parenthesis q close parenthesis equals 1 plus 3LQ plus 4L squared q squared plus open parenthesis 1 plus 4L cubed close parenthesis cubed plus open parenthesis 2 plus 5L cubed close parenthesis q to the 4th plus open parenthesis 1 plus 7L cubed plus L to the 4th close parenthesis q to the 5th plus open parenthesis q to the 5th plus open parenthesis 2 plus 7L cubed plus 2L to the 4th close parenthesis q to the 6th plus open parenthesis 2 plus 7L cubed plus 2L to the 4th close parenthesis q to the 7th plus open parenthesis 2 plus 2L to the 4th close parenthesis q to the 8th plus q to the 9th plus dot 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 close parenthesis.
That's a lot.
It is, yeah.
But it's really amazing how we got to this very elegant expression after all of those intricate calculations.
Yeah, it really is quite beautiful.
Yeah, so what can we actually take away from this?
So this function, it basically tells us a lot about the geometry of this curved singularity.
Okay.
Specifically, these coefficients are telling us about the number and the complexity of these strata at each level of the Hilbert scheme. And so it's kind of like a fingerprint.
For that particular singularity.
Exactly. Yeah.
So if we were to calculate the Motivic Hilbert Zeta functions for a bunch of different curved singularities,
right,
we could use them to see which ones are similar, which ones are different.
Exactly.
Cool.
Yeah.
So it's not just crunching numbers, we're actually revealing something.
Absolutely. Yeah.
About the structure of these singularities.
Yeah. And I think this is a great example of how powerful math can be.
Yeah.
You know, we started with this really abstract concept.
Right.
And then we were able to use logic and reasoning to figure out all this really detailed information.
Yeah. And it's all connected.
It is. Yeah. And this is just one example.
Right.
You know, there are so many other things that we could explore.
Yeah.
That are related to this.
Well, thank you so much for taking us on this deep dive.
Yeah, of course. It was my pleasure.
It's been amazing. And to all of our listeners out there, thank you so much for joining us. And we'll be back soon with another deep dive. Welcome to another deep dive. Today, we're going to be tackling some fascinating math.
Oh, yeah.
Specifically, we're going to be trying to understand curved singularities.
Okay.
Through the lens of the Motivic Hilbert Zeta function.
Sounds fun.
Our source material is a recent research paper that dives into a new algorithm for computing this function.
Oh, okay.
Specifically for curves that have something called a monomial local ring.
Right.
So buckle up because we're about to venture into the world of abstract algebra and geometry.
What makes this deep dive particularly interesting is that the Motivic Hilbert Zeta function acts like a powerful lens, revealing intricate details about these singularities.
Okay.
It goes beyond traditional methods, giving us a much finer-grained understanding of the geometric structure of these curves.
Okay, so let's unpack this a little bit.
Yeah, sure.
I understand that a singularity is basically a kink in a curve.
Right, it's a good way to think about it, yeah.
But what exactly is the Motivic Hilbert Zeta function?
So, imagine you're trying to describe a complex shape, but you can only use a limited set of building blocks.
Okay.
The Motivic Hilbert Zeta function provides a way to encode information about the singularity using a specific set of mathematical objects, elements from something called the Grothendieck ring of varieties.
So instead of just looking at the shape itself, we're breaking it down into its fundamental components.
Exactly. And this breakdown is sensitive to the presence and nature of singularities, giving us a more complete picture compared to other methods.
Now, the paper specifically focuses on monomial curves, which apparently have a unique property that makes them easier to work with.
Absolutely.
Can you elaborate on that?
Monomial curves have a local ring that can be expressed in a particularly nice form. It's written as C and then double brackets. See the alpha one, and then a comma, and then all the way up to T to the alpha E, and then close the double brackets. This structure makes them a great starting point for tackling the challenge of computing the Motivic Hilbert Zeta function.
So it's like having a simplified model that allows us to develop and test our methods before tackling more general cases.
Exactly.
So tell me about this new algorithm that they've proposed. How does it actually work?
Their approach is quite clever.
Oh.
They leverage a tree structure associated with something called the valuation semigroup of the curve.
Okay.
This tree helps to systematically organize and understand the possible subsemi-modules,
Okay.
which are essential for calculating the zeta function.
Hold on, a tree structure. Can you break that down a bit further?
Yeah.
Sounds like we're branching out into combinatorics here.
You're right. There's a definite combinatorial flavor to this. Think of the valuation semigroup as a set of numbers that encodes key information about the curve.
Okay.
The tree structure provides a way to visualize and navigate the relationship between different subsets of this semigroup, which we call subsemi-modules.
So each branch of the tree represents a different subsemi-module.
Precisely.
Okay.
And the way these branches connect reveals crucial information about the geometry of the curve, particularly around the singularity.
That's really cool. It sounds like this algorithm is a powerful tool.
Yes.
For exploring those hidden geometric connections.
It is.
What other key steps are involved in this process?
One of the most intriguing aspects of the algorithm is the use of something called piecewise vibrations. This concept allows us to relate different branches of the tree, or different subsemi-modules, in a geometrically meaningful way.
I see.
It provides a lens to understand how different parts of the Hilbert scheme, which is a space that parameterizes all the different subschemes of the curve, are connected.
So it's like finding hidden pathways between seemingly separate parts of our geometric landscape.
Exactly. And those pathways hold the key to unlocking the secrets of the Motivic Hilbert Zeta function.
Wow.
Another crucial element is the concept of syzygies, which are pronounced A-si-z.
It's these.
These.
Yes. These describe mathematical relationships between the generators of a subsemi-module. The algorithm utilizes these relationships to compute the class of each stratum in the Grothendieck ring, contributing to the final calculation of the zeta function.
I'm starting to see how all these pieces fit together.
Good.
But it's definitely a lot to wrap my head around.
Oh, no, it's a lot.
To help solidify things.
Sure.
Can you tell me about a specific example where they successfully applied this algorithm?
They tested their algorithm on a curve called the type W8 curve, which has a local ring that can be represented as C double brackets, T to the fourth, T to the fifth, T to the sixth, close double brackets. They were able to successfully compute the Motivic Hilbert zeta function for this case, demonstrating the effectiveness of their approach. That's impressive.
It is.
So they've not only developed this sophisticated algorithm, but also proven that it works in practice.
They have.
It's like a mathematical treasure map leading to a hidden gem of geometric insight.
Indeed, it's a testament to the power of their approach. And remember, example 3 from the paper really highlights the non-trivial nature of a particular condition. It's denoted as sigma sub I, and then this kind of like a curly less than symbol, and then gamma in corollary 1.
I see.
That arises when dealing with scissor-kinjis. It showcases the subtle complexities involved in these calculations.
Right. Even in the seemingly abstract world of mathematics, there are always unexpected twists and turns.
You said it.
Now, before we dive deeper into the specifics of the algorithm, let's take a step back and revisit the theoretical foundation that underpins this entire endeavor.
Sure.
I think it's important to understand the broader context before getting lost in the weeds of computation.
I agree. Welcome back to our deep dive into the Motivic Hilbert zeta function.
I'm ready to keep going.
All right. Now that we've laid the theoretical groundwork, it's time to roll up our sleeves and explore how the algorithm actually works.
I'm excited to see these abstract concepts translate into concrete steps.
I think you'll like it. Algorithm 1 serves as the main framework, right? It takes as input a curve singularity C with valuation semigroup, written as the capital Greek letter gamma equals angle brackets, alpha 1 comma, all the way up to alpha E, close angle brackets, and it's conductor C. A measure of the curve's singularity level. We discussed using the truncated set, written as a capital Greek letter gamma with a greater than or equal to n subscript for practical computation. With the paper suggesting n equals, in parentheses, c minus 1, close parentheses, times, in parentheses, alpha 1 plus 2, close parentheses, based on their derived bounds. The output of algorithm 1 is the Motivic Hilbert zeta function itself, expressed as z, with a Hilb superscript, and then C, O subscript Q, equals the sum over delta in square brackets. C, open square bracket, delta, close square brackets, times q to the L, in parentheses, delta, close parentheses.
Right, so that function encapsulates all of the geometric information
Well, it does.
that we were trying to find about the curved singularities.
Right.
Where does the algorithm begin?
It starts by initializing a set,
Okay.
D sub 1.
E sub 1?
Yes, with the subsemi module delta sub 1, which is just the valuation semigroup without 0.
Okay.
So we can write that as delta sub 1 equals gamma backslash open curly bracket 0 close curly bracket, which equals, in parentheses, alpha 1, all the way up to alpha e, close parentheses.
Okay.
Then, using algorithm 4, which we'll get to later,
Okay.
it generates the sets d sub 2, d sub 3, and all the way to d sub c.
Right, so it's like we're gathering all the ingredients before we start cooking.
Precisely.
Okay.
These sets contain all the necessary subsemi modules for computing the zeta function. The core of the algorithm is a loop
Okay.
that iterates over L from 1 to C,
I see.
calculating each coefficient term,
Yeah.
open square bracket, C sub L, close square bracket, equals the sum over delta, which is an element of D sub L, of open square bracket, C sub delta, close square bracket,
Okay.
of the Motivic Hilbert zeta function.
So it's systematically going through each level of the Hilbert scheme
But it is.
and computing its contribution to the overall function.
Exactly. Inside this loop for each subsemi module,
Okay.
which is the lowercase Greek letter delta
Okay.
in the set D sub L,
Okay.
the algorithm does the following.
Right.
So first, it computes the Frobenius element of delta, gamma sub delta,
Okay.
the largest element of gamma not in delta. It uses algorithm 2 to find the minimal generators of delta as a module over gamma, storing them in the set T sub delta, which equals open curly bracket gamma 1 all the way up to gamma m, close curly bracket.
Okay.
Algorithm 3 is called to compute the syzygy module of delta. Sys is open parenthesis, delta, close parenthesis,
Okay.
capturing the relationships between delta's minimal generators.
I see.
It determines the minimal generators of sys in parentheses, delta, close parentheses, storing them in a set T sub sys, open parenthesis, delta, close parentheses, equals, in curly brackets, sigma 1, all the way up to sigma n, close curly brackets.
Okay.
It constructs the subsemi module M, in parentheses, delta, close parentheses, by adding the Frobenius element gamma sub delta to delta.
So we're finding the Frobenius element,
Yes.
the minimal generators of both the subsemi module and its syzygy module,
Right.
and then constructing a new subsemi module by adding the Frobenius element.
Exactly.
Okay, what happens next?
The algorithm then calculates two crucial counts.
Okay.
The first one is C sub 1. This is the number of minimal generators of delta that are strictly less than gamma sub delta.
Okay.
The second one is C sub 2.
Correct?
This is the number of minimal generators of sys, in parentheses, delta, close parentheses, that are both strictly less than gamma sub delta and satisfy the condition, sigma sub I, and then the curly less than symbol, and then gamma sub delta. And if you recall, these counts are directly used in corollary 1
Right.
to compute the class of the stratum.
Yeah.
C open square bracket, delta close square bracket in the Grothendieck ring.
Right. That formula ties everything together.
It does.
Once the algorithm iterates through all the subsemi modules in D sub L,
Okay.
it sums their contributions to get the coefficient term, open square bracket, C sub L, close square bracket.
Exactly.
This process repeats for all L from 1 to C.
Right.
So it's like building the zeta function piece by piece, level by level.
A perfect analogy.
Yeah.
Finally, the algorithm assembles the complete Motivic Hilbert zeta function by combining all the coefficient terms,
Okay.
resulting in Z with a Hilb superscript and C O subscript Q equals 1 plus the sum from L equals 1 to C of, in square brackets, C sub L, close square brackets, times Q to the L.
Okay, I'm starting to get a better grasp of how algorithm 1 orchestrates this intricate computation.
Good.
Now, let's dive into those sub-algorithms that do the heavy lifting.
Okay.
Algorithm 2, if I recall correctly, finds the minimal generators of a subsemi module delta
Yes.
as a module over the valuation semigroup.
That's right.
It takes the curved singularity C with its valuation semigroup and conductor
Right.
along with the subsemi module delta.
Okay.
Crucially,
Yeah.
it assumes that delta is represented as a sorted list of elements.
Okay.
Delta equals, in curly brackets, a sub 1 all the way up to a sub s, close curly brackets, where a sub I is strictly less than a sub I plus 1.
Right.
This sorting list representation seems to be a recurring theme, doesn't it?
It is, yeah, it simplifies things. Algorithm 2 starts by initializing a set T sub delta with the first element of delta, which is a sub 1,
Okay.
which is guaranteed to be a minimal generator.
Right.
Then it iterates through the remaining elements of delta,
Okay.
checking if each element can be expressed as a sum of an existing minimal generator in P sub delta and an element from the valuation semigroup.
So it's like sifting through the elements,
Yes.
identifying those that can't be built from the existing minimal generators.
Exactly. If an element, I can't be expressed in this way,
Okay.
it's a new minimal generator
I see.
and is added to the set T sub delta. This process continues until all elements of delta have been considered,
Okay.
resulting in a complete set of minimal generators for delta.
Okay, that makes sense.
All right.
Now, what about algorithm 3?
Okay.
It's all about computing the syzygy module of a subsemi module, right?
That's right.
Okay.
Algorithm 3 unveils the relationships
Yeah.
between the minimal generators of delta, providing insights into the subsemi module structure.
I see.
It takes the same inputs as algorithm 2.
Okay.
Curve singularity, its valuation semigroup, the conductor,
Great.
and the subsemi module delta.
Okay.
And also requires the set of minimal generators of delta,
So-
P sub delta,
Right.
which is conveniently computed by algorithm 2.
Right. So we're building upon the results of the previous algorithm.
Right.
What happens next?
Algorithm 3 initializes an empty set, syzes, open parenthesis, delta, close parenthesis,
Okay.
to store the elements of the syzygy module.
Okay.
It then iterates through the elements of delta,
Right.
checking for each element.
Yeah.
If it can be expressed as a sum of two distinct minimal generators from T sub delta and elements from the valuation semigroup.
So we're looking for elements that can be formed by combining different minimal generators.
That's right.
What if we find such an element?
If an element satisfies this condition,
Okay.
it indicates a non-trivial relationship between the minimal generators. And we add this element to the syzygy module, syzits, open parenthesis, delta, close parenthesis.
Right.
This continues until all elements of delta are checked,
Oh, right.
resulting in a complete description of the syzygy module.
That's starting to become clear.
Yeah.
Now, what about algorithm 4?
Algorithm 4.
Yeah, it's the one responsible for building that tree structure G sub gamma.
That's right.
Right.
Nice. Okay.
Algorithm 4 takes the curved singularity with its valuation semigroup and conductor as input.
Okay.
And its output is a series of sets D sub L for L equals 1 up to C.
Okay.
Each set contains all subsemi modules of gamma
Okay.
that differ from gamma by exactly L elements.
Okay.
The algorithm initializes the set D sub 1 with the subsemi module delta sub 1, which equals, in parentheses, alpha 1 all the way up to alpha E, close parentheses,
Right.
the valuation semigroup without 0.
Right.
Then it enters a loop,
Okay.
iterating from L equals 1 to C minus 1,
Oh, okay.
sequentially constructing the sets D sub 2, D sub 3, all the way to D sub C. So it's systematically building the tree level by level.
Exactly. For each level L,
Okay.
the algorithm goes through each subsemi module in D sub L.
Okay.
For each subsemi module delta in D sub L,
Yeah.
it computes the set of minimal generators T sub delta.
Right. And then for each minimal generator in T sub delta, we create a new subsemi module, right?
Exactly.
Right.
For each minimal generator gamma sub I in T sub delta, a new subsemi module delta sub I is constructed by removing gamma sub I from delta.
Okay.
This new subsemi module delta sub I
Yeah.
is then added to the set D sub L plus 1,
Okay.
representing the next level of the tree.
Okay.
This process continues until all levels of the tree are constructed.
Wow, it's fascinating how this algorithm mimics the branching structure of a tree
It is, right?
to organize these subsemi modules.
It is, yeah.
Now, are there any specific implementation details or assumptions we should be aware of?
One key detail
Okay.
is the assumption of sorted list representation for subsemi modules. This allows for efficient operations like deletion of minimal generators, which can be done in constant time,
Okay.
or written as a big O of 1,
Okay.
significantly impacting the overall efficiency of the algorithm.
I see. So while these algorithms seem quite intricate,
They are, yeah.
they've been carefully designed with efficiency in mind.
They have been, yes.
Okay.
Every step has been meticulously crafted, taking advantage of the underlying mathematical structures to ensure computational feasibility, especially when dealing with complex curves.
This walkthrough has been incredibly insightful.
I'm glad to hear that.
I'm starting to appreciate the elegance and complexity of these algorithms.
Good.
I'm eager to see how they're applied to a concrete example in the paper.
Yeah, that's what we'll do next. Welcome back to the final part of our deep dive.
I'm excited to see it all come together.
All right, we've journeyed through the theoretical landscape
Yeah.
and explored the intricate machinery of the algorithm. Now, let's witness how these algorithms come alive in a concrete example.
I'm eager to see how they apply all of this to a specific case.
Okay.
They focus on the curve singularity with the local ring C, double brackets, 10 to the 4th, comma t to the 5th, comma t to the 6th, close double brackets.
Precisely.
Okay.
This curve has a valuation semigroup.
Okay.
Gamma equals, in angle brackets, 4, 5, 6, close angle brackets.
Okay.
And a conductor C equals 8.
Go.
Using theorem 3, we set n equals, in parentheses c minus 1, close parentheses, times, in parentheses, alpha 1 plus 2, close parentheses, which equals 42, and work with the truncated set, gamma sub greater than or equal to 42 equals, in curly brackets, 0, 4, 5, 6, 8, close curly brackets, union in square brackets, 9, 42, close square brackets.
Okay.
No.
So the first step is to use algorithm 4 to generate those sets, D sub L, which contain all the subsemi modules of gamma that differ from gamma by exactly Clemiel element. What do those sets look like for this particular curve?
So D sub 1 equals, in curly brackets, open parenthesis, 4, 5, 6, close parenthesis, close curly brackets.
Okay.
D sub 2 equals, in curly brackets, open parenthesis, 5, 6, 8, close parenthesis, comma, open parenthesis, 4 curly brackets. D sub 3 equals, in curly brackets, open parenthesis, 6, 8, 9, close parenthesis, comma, open parenthesis, 5, 8, close parenthesis, comma, open parenthesis, 5, 8, close parenthesis, comma, open parenthesis, 5, 6, close parenthesis, 4, 11, close parenthesis, close curly brackets. D sub 4 equals, in curly brackets, open parenthesis, 8, 9, 10, 11, close parenthesis, comma, open parenthesis, 6, 9, close parenthesis, comma, open parenthesis, 5, 12, close parenthesis, comma, open parenthesis, 4, close parenthesis, close curly brackets. D sub 5 equals, in curly brackets, open parenthesis, 9, 10, 11, 12, close parenthesis, comma, open parenthesis, 8, 10, 11, close parenthesis, comma, open parenthesis, 8, 9, 11, close parenthesis, 8, 9, 10, close parenthesis, comma, open parenthesis, 6, 13, close parenthesis, comma, open parenthesis, 5, close parenthesis, close curly brackets.
Okay.
D sub 6 equals, in curly brackets, open parenthesis, 10, 11, 12, 13, close parenthesis, comma, open parenthesis, 9, 11, 12, close parenthesis, comma, open parenthesis, 8, 11, close parenthesis, comma, open parenthesis, 19, 11, close parenthesis, comma, open parenthesis, 8, 11, close parenthesis, comma, open parenthesis, 8, 10, close parenthesis, 8, 9, close parenthesis, comma, open parenthesis, 6, close parenthesis, close curly brackets. D sub 7 equals, in curly brackets, open parenthesis, 11, 12, 13, 14, close parenthesis, comma, open parenthesis, 10, 12, 13, close parenthesis, comma, open parenthesis, comma, open parenthesis, comma, open parenthesis, 10, 11, 12, close parenthesis, comma, open 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 parenthesis, close curly brackets, and finally D sub 8 equals, in curly brackets, open parenthesis, 12, 13, 14, 15, close parenthesis, comma, open parenthesis, 11, 13, 14, close parenthesis, comma, open parenthesis, 11, 13, 14, close parenthesis, comma, open parenthesis, 11, 12, 13, close parenthesis, comma, open parenthesis, 10, 13, close parenthesis, 9, close parenthesis, 10, 12, close parenthesis, comma, open parenthesis, 10, 11, close parenthesis, comma, open parenthesis, 9, 16, close parenthesis, comma, open parenthesis, 8, close parenthesis, close curly brackets.
That's quite a collection of subsemi modules.
It is.
Algorithm 4 did a thorough job of mapping out the structure.
It did a good job.
Now we need to calculate the class of each stratum. C, open square bracket, delta, close square bracket, in the grothendec ring using algorithm 1 and corollary 1. Right.
Yes. This involves finding the minimal generators of delta.
Okay.
And cis, open parenthesis, delta, close parenthesis, the Frobenius element, gamma sub delta, and the counts C1 and C2. Remember, those counts are essential for applying corollary 1.
That formula ties everything together beautifully.
It really does.
So, after all those calculations, what does the Motivic Hilbert Zeta function look like for this specific curve?
So open square bracket C, open square bracket 1, close square bracket equals 1. Open square bracket C, open square bracket 2, close square bracket equals 1 plus L squared. Open square bracket C, open square bracket 3, close square bracket equals 1 plus L plus 2L squared. Open square bracket C, open square bracket 4, close square bracket equals 1 plus L plus 2L squared plus L cubed. Open square bracket C, open square bracket 5, close square bracket equals 1 plus L plus 2L squared plus 2L cubed, open square bracket. C, open square bracket 6, close square bracket equals 1 plus L plus 2L squared plus 3L cubed plus L to the fourth.
Okay.
Open square bracket C, open square bracket 7, close square bracket equals 1 plus L plus 2L squared plus 3L cubed plus L to the fourth. And open square bracket C, open square bracket 8, close square bracket equals 1 plus L plus 2L squared plus 3L cubed plus 2L to the fourth.
Each of those expressions represents the contribution from a specific level of the Hilbert scheme.
Yes.
And by combining them, we get the complete Motivic Hilbert Zeta function.
Right.
Right.
Exactly. For this curve singularity. It's Z with a Hilb superscript and COO subscript Q equals 1 plus the sum from L equals 1 to 7 of open square bracket C open square bracket L close square brackets times Q to the L plus open square bracket C open square bracket 8 close square brackets times in parentheses Q to the 8th plus Q to the 9th plus ... close parentheses.
That's an impressive result.
It is impressive.
It really showcases the power of their algorithm to provide concrete, explicit formulas
Absolutely.
for these intricate geometric objects.
It does.
This entire deep dive has been incredibly illuminating.
It has been.
We started with these seemingly abstract concepts, singularities, Hilbert schemes, growth-endic rings,
Right.
and saw how they all weave together to reveal a deeper understanding of curve geometry.
And what's especially exciting is that this research opens up new avenues for exploration.
They specifically mentioned that their work focuses on planar curves.
Right.
Could this algorithm be extended to curves in higher dimensions?
That's a great question.
Yeah.
Extending the algorithm to higher dimensions would undoubtedly present new mathematical challenges and require a deeper dive into the geometry of singularities in higher dimensional spaces.
Yeah.
It's a fertile ground for future research.
It's a reminder that even with such significant breakthroughs,
Yes.
there's always more to discover and explore in the world of mathematics.
There is.
And they've generously provided a Python implementation of their algorithm,
Yes, they have.
which is a fantastic resource for anyone who wants to experiment
Absolutely.
and gain a deeper understanding of how it works in practice.
I agree.
I encourage our listeners to check out those links in the show notes.
Yes, you should.
It's a great way to get hands-on with this groundbreaking research.
Well, I think we've reached the end of our journey into the fascinating world of the Motivic Hilbert Zeta function.
It's been an incredible experience.
It has been.
From unraveling complex mathematical concepts
Yeah,
to witnessing the elegance of their algorithm,
right.
this deep dive has truly enriched our understanding.
I hope our listeners have come away with a renewed appreciation for the beauty and power of mathematics, even in its most abstract forms.
Right.
There's always more to learn, more connections to uncover, and more mysteries to unravel in the vast universe of mathematical knowledge.
So, until our next deep dive,
Yes.
keep exploring, keep questioning,
Yes.
and keep the spirit of mathematical curiosity alive.
Absolutely.